this short video, I'll describe the different isotopic forms of carbon and how isotopic compositions are calculated and reported. From a mass balance perspective, carbon accounts for nearly half of the dry mass of every organism. These carbon atoms create the backbones for proteins, lipids, and carbohydrates. And a quick look at the periodic table shows that the atomic number of carbon is 6, which means that every carbon atom contains 6 protons. Note that the atomic weight of carbon, which is the sum of the protons and the neutrons, is 12.011. Now this non-integer number means that the number of neutrons in different carbon atoms can vary. 99.9999% of naturally occurring carbon is stable. That means it's not radioactive. So I won't be discussing carbon-14, the radioactive isotope of carbon, today. Now this stable carbon comes in two isotopic forms that we call carbon-12 and carbon-13. The vast majority of the carbon that we encounter is carbon-12, which consists of atoms that contain 6 protons and 6 neutrons. The remaining carbon, about 1.11% of it, is carbon-13, which consists of 6 protons, but it has 7 neutrons. Now this extra neutron makes carbon-13 a little bit heavier, but it also makes carbon-13 an excellent tracer atom for biochemical studies because we can measure its abundance with great precision. The nomenclature for reporting stable isotope concentrations dates back to the work of the early geochemists in the 1950s. And unfortunately today, it creates a little confusion for many folks entering the field. So the concentrations of heavy isotopes are reported in units that we call delta values. They're represented using this lowercase Greek symbol for delta. Now to calculate delta values, the ratio of the numbers of carbon-12 and carbon-13 atoms in an unknown sample is subtracted from the ratio of carbon-13 to carbon-12 atoms in an international standard. In this case, this international standard has an isotope ratio of 0.112372. Now, this resultant is then divided by that ratio and then multiplied by 1,000. Why? Because if you don't multiply it by 1,000, we get real small numbers, and humans don't like small numbers. So the standard for carbon that was originally based on a geological formation of fossilized mollusks called P.D. belemnite. This is found in South Carolina, but scientists ran out of this original standard, and now a new synthetic international standard called VPDB is used, and this stands for Vienna P.D. belemnite. The standardized carbon-13 concentrations are written in a form using this symbol that we call per mil. Simply, the international standard has a value of 0 per mil. Note that per mil is not parts per million, or ppm as we typically think, nor is it parts per thousand as you see in other fields of science. And a typical mouse might have a carbon-13 value of around -16 per mil, depending on what it eats. In simple terms, this means that the carbon in its body and in its breath, as it oxidizes the materials in its body, has a slightly lower concentration of carbon-13 than the ancient fossil. So Celsius, often used by biologists, and Kelvin, used by physicists or chemists, represents two scales for measuring temperature. And those units can be interconverted depending on the convention. But the same is true, fortunately, for measures of stable isotopes, where geochemists and ecologists tend to use delta values, and some clinical biologists use a unit called atom percent, abbreviated AT%. The first of these two equations shows how atom percent can be calculated if we know the isotope ratios and we know the delta values. Second equation shows how we can back calculate for delta values if we know the isotope ratios and the atom percent. Now I mentioned that the VPDB standard has a value of 0 per mil. This is equal to about 1.111 atom percent. Carbon samples that have negative delta values are said to be depleted in carbon-13. I'll discuss the biochemical mechanisms for this in another talk, but most of the carbon that you encounter day to day will be isotopically light and have negative delta values. For example, the CO2 in the atmosphere has a value of about -8 per mil. Your average mouse, if it's consuming a corn-based diet, corn is a C4 plant, might have a value of -16 per mil. If you take that same mouse and raised it on a rice-based diet, it might have a value of -24 per mil. Fossil fuels tend to be very depleted in carbon-13 with values of -60 per mil or less. In tracer studies, the delta carbon-13 values can also be positive. Such samples are said to be isotopically enriched or hot. Not radioactive, but hot in the sense that they have more carbon-13 than naturally occurring materials. There are thousands of different carbon-13 tracer molecules that are commercially available for use in tracking biochemical processes in vivo. The bottle shown here is filled with carbon-13 labeled glucose, and it's at a concentration of 99 atom percent. This is equivalent to about 8.8 million per mil, and that's why sometimes per mil delta units are not all that useful. Now I mix my own carbon-13 enriched standard that has a value of about 4,000 per mil. This is equivalent to an atom percent of just over 5%. And that covers pretty much all bases for tracer studies. And what this means is that there's an enormous range of isotope space that we can use for carbon-13 tracer studies. In a follow-up video, I'll discuss various measurement techniques, different types of tracers that you can choose from, and different experimental approaches for metabolic tracer studies.